Hello world, it's me. When working on vintage logic systems, you will frequently see fixed logic inputs that are tied up to the 5-volt rail through a resistor, like here on the schematics for this Intel microscope 820. And sometimes quite unexpectedly, you might even see something rather than just a logic gate, but like a higher order device. Like here's a 74 LS193 that's tied up, the load on both of these is tied up again through a resistor to the 5-volt rail. This practice is fairly uncommon today, which begs the question, what did we know back then, or maybe what didn't we know, that would lead us to have such a strange habit of tying fixed inputs high through a resistor rather than just taking them to 5 volts? And should current design still be following this practice, or does it deserve the standard, okay, boomer type of dismissal? Now, in a few instances, it's convenient to tie the inputs high or low of a device through the resistor so that you can come back later and manually set something to the opposite state when you're doing diagnostics, or if this is a prototype board or something like that. So for example, in this case, we've got a little latch. The set and the reset are both tied high through a resistor, but we have a little test point here that we can run a jumper to ground so that if we want to manually set or clear this output, we can do that because, we're not going to short this out because it's protected by that resistor. So this isn't the kind of situation that I'm talking about. And likewise, I'm not talking about whether we need to have all of the inputs on a design tied high or low. This is not about if we have an unused input, that would just be like a TTL, and we know that that TTL by itself is going to float high. But regardless, even if we know that's going to float high, we need to explicitly tie that high. So to be clear, this is not a question if unused inputs need to be tied to something, either high or low, to prevent them from being indeterminate. We should all agree that no inputs should be left uncommitted, and it's critically important that all fixed inputs be tied high or low as required by the circuit and not allowed to just float. Generally we would take unused inputs of ANDs and NANDs high and take ORs and NORs low. And likewise, we should be in reasonable agreement at least that it's best practice that if we have a unused gate inside a device, we should probably take enough of their inputs either high or low to eliminate the possibility of that device from oscillating. For example, here's a schematic for a Prologue STD 7803A. And so we can see, as in common in a lot of schematics, there's a little area down here of unused gates. So these are leftover gates in some of these devices. You can see these buffers, they have them taken the inputs low so that they're not going to oscillate. And here's a little latch that they have the reset taken low so that they know that this is constantly in a state of reset, so it's not going to oscillate. So while it's okay in prototypes to leave these uncommitted so you can come back and use them, but when you're going to production, anything that's an unused gate should be tied one way or the other so that it can't oscillate. But this video isn't about that either. The question is this: in digital design, if we have an input, like for example in these 3 input NORs, that we don't need to use, so we're going to take it high, when do we have to take that high through a resistor? And when can we take something high like it is down here in the 74-193 where it's just taken directly high to the positive rail? This is something that you don't see very often. So I think this is worth a video, and here goes. The short answer is this. If you're tying something down to common, you can go through a resistor if you want, but it's optional, and only with a few exceptions, tying it directly to the common rail is much preferred. However, when you're tying something high, that's when the question comes in. It's much less straightforward. But there is generally a reasonably simple explanation, and that is that if you have a multi-emitter input to any device, whether it be a gate or whether it be an input on a counter or a latch or something like that, if that is a multi-emitter input, then it should not be tied directly high to the 5-volt rail. It should always be tied high through a protection resistor. And we can go back. We're going to refer to a couple of data books. This is the TTL data book for design engineers from Texas Instruments, and this is the microelectronics data book from Motorola. And in the microelectronics data book from Motorola, in 1970 and 71, Motorola specified that all of their fixed logic 1 inputs need to be tied high through a 1K resistor, not just multi-emitter inputs, but all of their inputs. We'll see a little bit more on that when we start looking at some of the TTL data sheets in the Motorola catalog. But if we just look at their little introduction here on TTL, for Motorola we can see the following. In paragraph 2.6 they say that for the generation of a logic 1 on a fixed input, ideally you should use the output of an unused gate. Okay, that makes sense. Otherwise, you can use VCC if power spikes are guaranteed to never exceed 5.5 volts. But generally, a tie-up input should include a 1 kilo ohm current limiting resistor to VCC. Now in the TI data book, at nearly the same time, they were saying that this was only required for multi-emitter inputs and not for all devices. So Motorola was saying all inputs. TI was saying only if it's a multi-emitter input. And during the same period of time, National Semiconductor was completely silent on the issue. They weren't saying anything about unused inputs at all. Fairchild had an interesting little bit. We'll come back to looking in their data book a little later in the video. So already in 1970, we were seeing a divergence among the manufacturers' recommendations. National Instruments had their head in the sand. These guys were saying tie everything through a resistor, and these guys were saying only if it's a multi-emitter input. So my rule of thumb is as follows. If the input's multi-emitter, then the input should always be tied up through a resistor, and otherwise it's generally okay to just tie it directly to VCC. Now in terms of the logic family, if it is 74 LS or later, so 74 LS, ALS, and so forth, we're exempt from that, so we don't have to tie that up, because as we'll see later, their inputs are completely different than the input to a normal TTL. So if all you wanted to know was when and how you need to tie the inputs high through a resistor, then that's it. Thanks for watching. Please like and subscribe if you feel so inclined. But if you want to know why, then let's proceed, as Paul Harvey used to say, with the rest of the story. But first, this little groundwork. Here's a book from TI, Designing with TTL Integrated Circuits. And let's look at the original 7400 TTL gate. This input, Q1, is the current steering transistor. So when the input is low, the current's going to the left and out the low emitter, and when the inputs are all high, the current is steering to the right and going to the next stage, which is Q2 in this figure. As you can see in this diagram, for this particular device, the current steering input transistor is a multi-emitter transistor, meaning, somewhat obviously, that there's more than one emitter in that conduction path. So let's compare that to an OR gate. Here's an OR gate. We can see in the OR gate, each input has its own transistor. So these are just your standard single emitter transistors on each input, where on the AND gate or the NAND gate, these are inputs going into a transistor that has more than one emitter. Let's look at these multi-emitter devices. From the side or cross section, meaning cut through the device, there's going to be an N channel that's implanted and its terminal. That's going to be, let's say, the collector. Then there's going to be another N channel and its connection. That's going to be the emitter. And those are sitting in this bathtub, say, of P-channel material. And then its connection, and then that's the base. But there's no reason in this device why we can't implant another N channel, put a connection on it, make another emitter and another N channel and emitter, and as many of these as we wanted to, and those would all be in this same P material. So what happens is it doesn't matter which of these emitters go low, you'll still get your base to emitter current, and that will put the entire device into conduction. And that happens no matter which of these emitters is taking the current. So we can have one or more or any number of these emitters low, and as soon as any of these emitters go low, this device turns on. As soon as all the emitters are high, then this device turns off. So with this one transistor, the designer is able to very conveniently and simply implement a logical NAND gate, having any number of inputs just by adding more emitters to that same junction. And you can take that to the extreme. Here's a 74133. This is a Shotkey version of it, which we'll see is a little bit different. But basically, we have a 13 emitter input here, where we've got 13 emitters in this 13 input positive NAND gate. And if any one of those is low, this device turns on. If they're all high, this device turns off. Now, when I said on and off, I should have been a little bit more accurate. The If we look at the transistor, this is the base, here's the collector, these are the emitters. When I say on, what I mean is that we're getting current from the base out to any emitter, and then that puts the entire device into conduction, so we then get our current out of the collector. But when this is in its reverse acting mode, or off, all of these are high, so these are all at logic 1, and then what's happening is we're getting current coming out of the emitter into the collector, and that takes the collector high, and that collector, of course, is connected to the base of the next stage. So we're not interested in the next stage, we're only interested in this first input stage where we have these multi-emitter inputs. So let's look at these emitters again and get to the base of what the problem is. The first thing is that in order to get these to work, this emitter-base junction has to be much thinner than usual. So when they build this junction is very thin. The second thing to note is that between each of these emitters, you remember this is P material up here. So between each emitter we have an NPN junction. So if we just look at that, our normal, the NPN junction that we're thinking of, here's our N, this is our P, this is our N. So here's an emitter, and this is our base. So every one of these emitters, all 13 of those emitters in that 74, 133, whatever it was we were looking at, creates its own NPN junction. Now normally, just like it would in back-to-back diodes, these junctions are non-conducting because one of them is always going to be reverse biased. But you can guarantee that if we put enough potential across this, every reverse bias junction has its breakdown. And if there's a sufficient voltage, we'll get that breakdown, and then we can get avalanche conduction to occur across that reverse bias junction. So while the use of a multi-emitter junction is a great shortcut to make a NAND gate, it does present some other problems because of all of these NPN junctions. If these are all at logic 1, no problem. Current can come in and be shared by those and go out the collector. So all logic 1, no surprises, no problems. This is in its reverse active mode like you would expect. But now, when an input goes low, so let's take this one high, this one low, and this one high. Now this entire device is going to be in conduction, so we're going to get current coming from the base out this emitter. We're also going to get current coming from the collector out this emitter. Those are the two things that we planned for. And if our voltages are low enough, so we're below the breakdown voltage, this is just what we've got. We may have a microscopic amount of leakage current between the emitters, but basically that's all the current we're going to have. But as we approach that breakdown voltage, or as we exceed that breakdown voltage, what's going to happen is we now have a little bit of current leaking across each of these NPN junctions. So we're going to be coming out of this emitter, so current is being sourced by this emitter, and it's being drained out into this middle emitter. Now the higher we go above our breakdown, which the manufacturer has specified that 5.5 volts is going to be our breakdown voltage, the higher we go above that, the more current we're going to get leaking from these two emitters into that center low emitter. Now as it turns out, with all this current flowing everywhere, as long as this emitter-to-emitter voltage difference is not crazy high, according to the Texas Instruments data books, it's not so much a problem of permanent damage from the voltage breakdown, it's mostly a problem from current causing a temperature rise inside this device. So the rising temperature increases the beta, which causes more current to flow and so forth. And in the end, this current quickly becomes so large that the device can't dissipate heat fast enough, and that internal heating is what will destroy this device. And that's where the current limiting resistor comes in. So let's say in this case we wanted to take this guy high. So rather than coming from an upstream gate, this guy we're just going to take to 5 volts. If we had that shorted directly to the 5 volt rail, that rail gets a little spike on it that's higher than 5.5 volts, and now we've got as much current as we want from that 5.5 volts or 6 volts or whatever that spike happens to be coming in this emitter and sinking out this other emitter. But as we saw in those schematics, if we put a resistor in series with this, a 1K resistor, this is a current limiting resistor that throttles how much current can go into this emitter. So the manufacturers just specified that under worst case condition, we can have this guy sink all of the current that's coming from the base, all of the current that's coming from the collector, plus 1 additional milliamp that's leaking from all of the other emitters. So this is going to be the sum of the base current, the collector current, plus this 1 milliamp of leakage current. And they just built that in. When they designed this device, they said we can have 1 milliamp of leakage current, and that's where this is defined from. Now, some of the data books put a finer point on it. TI says that if it's a 74 or a 74H, it can handle 2 milliamps. But if it's a 74L, it can only handle half of a milliamp. But generally, they will just say that, okay, this 1K resistor is good enough. Now, remember that if you are using more than one emitter that's connected high, you don't want to have each of them have their own 1K resistor, or you could wind up getting 1 milliamp from that guy, 1 milliamp from that guy. So on a single device, all of these need to be connected together to that single 1K resistor. And this just kind of became a rule of thumb that when you had an input, if you obviously knew that it was a multi-emitter device, you would run it through a resistor, and in some cases it just became a habit that even if you didn't know if that was a multi-emitter device, just to be careful, you would run that through a resistor to pull up rather than just taking it to 5 volts. Of course, there was originally a bit of re-education needed for TTL because RTL, DTL, and ECL didn't suffer from the same problem because BUI hadn't invented the multi-emitter transistor until '61. We can look at the BUI patents. They're US 2985804 and 3283170. So in '61, which is when the first patent came out, BUI first specifies or first teaches about the multi-emitter transistor and subsequently the concept of transistor-transistor logic, although he called it TCTL for transistor-coupled transistor logic, which wasn't to be confused with DCTL, which is direct-coupled transistor logic. Sylvania came out and called it Sylvania Universal High-Level Logic, but it took Texas Instruments to give it the decent name of TTL that stuck, and just a simple, elegant name. So here in BUI's first patent, this is the 804 patent, you can see this multi-emitter device, and here's the 170 patent where we see the multi-emitter symbol in its currently present recognizable form. While only multi-emitter inputs had this problem, so typically AND and NAND gates, it just simply became a standard practice to put a current limiting resistor on any input that was tied high. And before going on, an additional note about BUI was that before he invented this, he was a lieutenant commander in World War II. He was in the Navy, and he earned the Distinguished Flying Cross and 4 Navy Air Medals. So after the war, he received his BS in electrical engineering from the University of Southern California, presumably on the GI Bill. And as with anyone's life, just try to imagine the ripple effects from fate's fickle finger. Here was a naval aviator in the middle of World War II who obviously was in combat, earning these medals. He survived, he went to college, and he invented what would become the workhorse of digital electronics for decades. We'll look at some Motorola circuits and we'll see that multi-emitters were hidden in all sorts of inputs. And a lot of manufacturers just didn't specify which inputs were multi-emitters. And so if they left out the diagram and they didn't show you diagrams in the data book, you would generally not know for sure what that input looked like, and it was just safer to always put the resistor in. Some designers preferred to tie each input high with its own resistor, like I showed earlier, or here's a ISBC 032, where we've got multiple inputs ganged together on one resistor, and TI in their data books, I think they said that you could have 25 inputs tied together. Motorola suggested you could have 35, but the number was very large, how many you could actually have tied together, because the high input current to a TTL is so low it could be handled by a 1K resistor very easy for many, many devices. Some like to have a little bit more panache in their designs. If we look at this in this Prologue one, here we can see that what they did was they took a unused gate. This is a 7432 OR gate. They take the inputs high and just tied to the rail, and these can be tied to the rail because this is not an AND or a NAND. It wasn't a multi-emitter device. It's not going to get damaged if there's a little bit of a spike on that. Tie those together, and they created a pull-up signal. They then take that pull-up signal around the board, and anybody that needs to have a logic 1, they would use that pull-up signal. So here we can see, here they've used the pull-up signal in this 74-138. Here's the pull-up signal in these 74 LS221s. They also went to a little bit more extreme. They took that pull-up signal, they ran it through an inverter and created a pull-down signal. And here we can see in this 138 again, there they utilized the pull-down signal. So they actually did the ideal thing, and I'm not knocking them. This is the safest thing to do, and that is to use a upstream gate to create the pull-up and the pull-down signals. This brings us to the point that's worth mentioning, and that is that this is only an issue with inputs that are tied to a rail and not inputs that come from another gate. The reason being that the totem pole or the open collector output from an upstream gate is already limiting the current sourcing, and it's already buffering its output from any transients on the rail. So I shouldn't have implied that Prologue was trying to show off here. This is technically the safest way to create this signal. And of course, when possible, you can avoid this altogether by anytime you have the opportunity, just take the signals together. Like here, instead of taking one of these high in this device, they just tied these two together. And so this is the other safe way of handling this. And in fact, this has a power advantage. If you look at the data book for your device, while it does specify that even for the multi-emitter devices, a logic 1 or a logic 0 will have 1 unit of load for each input. But if we look in the TI designing with TTL logic again, and I have seen this in the data books also, it's not just in this, but let's look at the input currents when emitters are tied together. So if we look at this device we just had showing here, this device, when we have the emitters connected together, what's its input current going to be? Well, it says the number of emitters tied together, 1, 2, 3, up to n, the total input current required. So if its input is logic low, the total input current required is going to be 1 times whatever the normal load is, no matter how many we have tied together. So in other words, when this is going to a logic low, no matter how many inputs we have tied together, the input is only as much current as would go into any single emitter. Unfortunately, if we go to a logic high, then it's just additive. So if we have 3 inputs tied together, when we're logic 1, it's going to be 3 times the input current for any particular input. Now I found this very, very interesting. In fact, it may seem like an aside, but I'm pretty sure that this is the most interesting part of this whole video. I doubt that anybody else really cares about this asymmetry between, inputs, emitters tied together between the logic low and the logic 1. But if you do happen to care and you think you know why this is not symmetric, let me know in the comments, or so we can compare our thoughts. I have some ideas about this, and I think this is just really an interesting thing. As another little aside, talking about the current on the inputs, you should note that when you're looking in the data book for the current values, keep in mind that those are under worst case but normal operating conditions. So they are not worst case avalanche breakdown conditions. They're worst case normal operating conditions. So whatever's in the data book for the low current, keep in mind there's going to be additional current coming. If you are over the breakdown voltage, you've got avalanche current coming up that emitter. If we look at a couple other places in this schematic, there's just some interesting things. One thing that I found interesting in this was, here Intel for the 74 LS37, they took this input directly to the 5-volt rail. They could get away with that because that's LS, and we'll look at the input of the LS a little bit later. Here on this 8755, they took the chip enable and the I/O read high through a resistor, and for that device, this is totally unnecessary. It even says in the data book that you don't have to do that. There's other places around in some latches where they would go through a resistor, and you just kind of scratch your head as to what their rhyme or reason was. But I think in most cases they were just being overly conservative in putting that resistor in. But it does surprise me that they were so bold here to take that guy directly to 5 volts. Here's a little assertion level logic going on, like I talked about in an earlier video. More assertion level logic. Intel was big on their assertion level logic on their schematics. Okay, so multi-emitter, straight 7400 TTL certainly had this problem, needed this protection. But then Shotkey devices came along. In 1970, although it was invented like 5 or 8 years earlier than this, in 1970 Texas Instruments introduced the Shotkey clamp TTL device. The question is, did a Shotkey device have more or less protection? First, let's look at what a Shotkey device is. Let me get another pen. So if we were to take this transistor and we put in here a forward biased Schottky diode to the collector. What it does is it clamps this current steering transistor and it keeps that transistor out of saturation. So when this is fully turned on, it can't go into saturation because rather than being allowed to go up to like 3/4 of a volt across this is going to keep it down to about 1/4 of a volt. So this can't go into saturation, and it makes this device much faster because then when we want to turn it off, we don't have to take all that stored charge back off of this again, because instead of allowing it to go up to 3/4 of a volt, we're held down here at 1/4 of a volt. So that's the advantage of this Schottky device. With much less charge to drain off the base, switching times are reduced, and much less power is wasted. So a 74S should have much less propagation than a straight 7400, say 5 or 6 nanoseconds compared to 10 nanoseconds, maybe twice as fast. So it gives it nearly the full speed advantage of ECL devices that came earlier, since that transistor is kept out of saturation just like in an ECL. But ECL, while it may be twice as fast, it took twice as much power as the Schottky. So the Schottky devices were an obvious advantage. But there's nothing new in here to protect the multi-emitter transistor from emitter-to-emitter current. In fact, it may have even been a little bit worse because now this base is going to be held at 1/4 of a volt. And I'm not sure if that would actually help or hurt this leakage current or this avalanche breakdown current between the emitters. If we go back to this designing with TTL integrated circuits, Schottky had come out by then. And so here's the regular transistor with a Schottky diode that's forward biased across it. And then this is the symbol for the Schottky device. You can see to note it, this is the Schottky transistor, and so it's got these little curly cues on the end just like you would on a Schottky diode. So on this, obviously all of the transistors are Schottky except for this output, which doesn't need to be Schottky because it can't go into saturation. And you can notice down here that the input clamps are now Schottky also. Now most Schottky devices have these reverse biased clamping diodes on the inputs, but these existed on earlier devices, particularly like this is the high-speed one. This is where these became really popular, to put these clamping diodes on the inputs. And then later when these all became Schottky, when they started making Schottky junctions in the device, they switched those over to Schottky clamping diodes. So obviously from here in the high-speed ones, this was 3/4 of a volt. Now we drop down to 1/4 of a volt on those clamps. Now these clamping diodes, by the way, were primarily to limit undershoot as the circuit speeds increase. They were not added to protect the inputs from overcurrent on these multi-emitter devices. So this was only to protect undershoot. So if you have a really high-speed device and you've got something that's switching state, and so you've got a lot of ringing when this is going below 0, and what those clamping diodes do is they clip all of that off. So it just eliminates it, so you don't have to get rid of that extra amount of current, and allows this to settle into its final value quicker. So that's why these clamping diodes became a problem when these circuits got faster and faster, and then it was just easy to build them in on the Schottky devices. So after the Schottky devices came the low power Schottky. Yeah, I think this one has a better diagram. So here we can see the progression. This is just a 7809, just a standard one. It does have clamping diodes, but it's multi-emitter. Here's the high-speed version, so lower resistances around, but still clamping diodes, multi-emitter. This is the straight Schottky, where this has gone into now it's a Schottky transistor, but still multi-emitter, and now these are Schottky clamping diodes. Everything's Schottky in this. This one doesn't have a pull-up. This is open collector. Then we go to low power Schottky, and we can see we've changed the design. Let's get a little bigger diagram of that. So here's a low power Schottky device. So we can see these are Schottky clampings, but here on the input, instead of having a multi-emitter transistor, we've gone back to diode transistor logic. So this is just a DTL input. So that's the same input that we had before TTL. If we look in the Motorola data book, this is the DTL section, and we can see all of these DTL devices. Now we can find a good one here. See, they're all just a diode input to that transistor. And so once they were able to make the Schottky junction on these devices and change that to a Schottky transistor, now we had diodes that were much faster than normal and had a much lower voltage. And so just from a operating perspective, it made more sense to go back to TTL with Shotkey than it does to continue making these multi-emitter devices. So that's why, as I said earlier, once we go to LS devices, and we can look in the LS data book, once we go to LS devices, all of these are going to be TTL type of inputs. Now, when I was digging in the old data books for a diagram here, I noticed an interesting tidbit from Fairchild. In the 1975 Fairchild TTL data book, here page 1-4, it specifies that LS TTL does not use multi-emitter input structure, which we've already seen in the TI data books. All Fairchild 9LS TTL, and 9LS is the Fairchild equivalent of just anybody else's 74LS, employs a DTL type input circuit. Yep, we saw that in the TI data books. So faster, increased input breakdown, blah, blah, blah. But let's look more at note 1. Note 1 says, this is 1975, the Fairchild 74LS03, 5, 22, 74, 109, 12, 13, 14 still use a transistor input at present, but will be redesigned by the first part of 76 to incorporate diode inputs. So what they're saying is when production catches up with current state of the art, these are going to switch over to diode inputs. Now when they say transistor inputs at present, I'm not sure if they mean single emitter inputs or if they mean multi-emitter inputs. But either way, they note that these gates will be redesigned first part of 76 to incorporate diode inputs like we saw in the TI data book. But the timeline must have slipped a bit, because if we look at their 78 data book, so the last one was 75, if we look at 78, Fairchild has not only included the gates that were in the previous list, but it's no longer just a footnote, and they've expanded this list of devices requiring the limiting resistor to include clock inputs of ripple counters, so the LS90, 92, 93, and so forth. And again, they use the term traditional emitter inputs are subject to damage. And I presume they mean multi-emitter inputs, or it is possible that, Fairchild single emitter inputs were just getting damaged, they were extra susceptible, and so they were just giving this warning. But unfortunately, Fairchild doesn't include any internal circuit diagrams in their logic data book, so we really don't know if these are multi-emitter or not. And that warning just kind of fades away when they come out with the 74F, or their fast family, in 1980. I just haven't been able to see where Fairchild mentioned again anything about these multi-emitter inputs. So it's possible that they were completely phased out by 1980. So that's one of the reasons why people just tended to put in these resistors in devices that they didn't know anything about, because something like this Fairchild comes along and says, hey, we still have, if you pull something out of stock and it was made the early part of 76, or in this case anytime in 78, it still needed a resistor on that multi-emitter input. So better safe than sorry in all of those. Okay, back to this one. So this is this TI data book for design engineers. It's 1973. 1973, so this is their rule of thumb. Unused inputs, and by unused they mean fixed inputs, of AND and NAND gates. Okay, so this is kind of the final rule of thumb, almost. We'll come across a little exception here in a bit. So this is the way you handle unused inputs to positive NAND and AND gates. Your first choice is to connect unused inputs to an independent power supply, okay, which is more regulated. But here they say that series 54LS, 54LS and 74LS devices with diode inputs may be connected directly to VCC. So if it's got diode inputs, you don't have to worry about this anymore. Second, connect to an output from an upstream device if you possibly can. Third is connect the unused inputs through a 1K resistor, and up to 25 inputs can be connected together. And then in D, take an unused gate and create a pull up and pull down like Prologue did in this schematic. Oops, not that schematic. Like Prologue did in this schematic. Just create a pull up, pull down with an unused device. So this is the TI way to handle unused inputs of positive AND and NAND gates. So this is where I started my rule of thumb I mentioned at the very beginning, where any straight 7400, 74H, 74L, and 74S has multi-emitter inputs that are obviously multi-emitter, it's shown in the diagram. They need to have that protection. 74LS, ALS, anything after that, I quit putting protection in unless it specifically said so in the data sheet. So those are the rules I lived by for a long time until I came across this. In the 1986 ALS and AS logic data book from Texas Instruments. We look at that exact same verbiage and it gets recomplicated. Okay, here's that exact same verbiage. Guidelines for gates and flip-flops using advanced Schottky TTL. Same thing, unused inputs of AND and NAND gates and unused preset and clear inputs of flip-flops. So now we have these same rules. The difference is on number 1, they took out the part about 74LS did not need to have this protection. So they're saying that even if it's an advanced Schottky for AND, NAND, gates, and unused presets and clears from the flip-flops, all required that resistor or this extra consideration in that voltage. So I found this the second most interesting thing. The asymmetry and the current was the most interesting thing. This was the second most interesting thing, was that in 86, now in the 84 data book this wasn't there, but this crept in sometime in the 86 data book. So for 15 years they had it with this verbiage, and they had it that LS could be exempt, and then suddenly in 86 they took that exemption for LS out and they added presets and clears on flip-flops. So the definitive answer we thought we had about AS and LS and ALS just went away. Let's look at one of those. Let's look at this. This is a flip-flop with the preset and clear, and we can get a little bit of an indication as to what's going on. We can see that the preset and the clear on this JK flip-flop just goes into 3 input AND gates. So both of those, the preset and the clear, are going into these 3 input AND gates. And the question is, when TI was designing these, did they simply use multi-emitter transistors for these AND gates rather than doing TTL inputs on these AND gates? And unfortunately, TI had stopped showing us the circuits. I think they may have, well, let's see, about 84 or so, they switched over to this new diagram, which I never really took a liking to for the logic diagrams. They stopped showing us the actual equivalent circuit internally, and they just went over and they show us these logic diagrams. So on TI, we really don't have any more information, but let's flip over to Motorola and look to see what their devices looked like for these same flip-flops. Okay, so here's the Motorola circuit internals for the 7476 flip-flop, and we can see there are multi-emitter transistors all over the device. You know, coming in 15, 15 is the output. So 15 is the output, goes into this multi-emitter. There's the set, the K input, over here the J input. All of these are going into multi-emitter devices that are coming to the outside world. So yeah, you can see where, you know, those would require protection because we've got a multi-emitter device coming straight from the outside world that has no protection. And if we look at other, you know, Motorola 7400s, you know, pretty much all of them had multi-emitter devices one way or another. There's the NAND gate, more NAND gate. You know, Motorola, we would see it in flip-flops. We would see some of their counters, some of their adders. A lot of them would have multi-emitter devices on inputs that you normally wouldn't suspect as having a multi-emitter transistor. So again, you know, it wasn't always obvious as to where you'd find these multi-emitter inputs. If they didn't show you the diagram, you know, sometimes you just wouldn't know for sure. And if all else fails, just put a resistor in. If we then go from the, what was this one? This one was 86. Yeah, this was the 86 data book. We go from the 86 data book. Next one I have is the 97 Designing with Logic Handbook, and here they're back to just specifying any multi-emitter input, and they leave the rest unsaid. Of course, here they've also got a typo in the section that says unused outputs of a device should not be left unconnected. So, you know, who can be sure at this point if anybody's actually proofreading these things? Or if technology and conventional wisdom actually went into retrograde in the mid-80s. Maybe that finally explains, you know, new Coke. So when tying up inputs, what's your practice? If you look in a schematic like this, you'll find all sorts of variances in this. Sometimes things are tied up when you wouldn't expect it. Sometimes things are tied up. And so even for someone like Intel, who normally was very conservative, some things just surprise me in these schematics. So what's your practice? You know, is this more of a rule or a recommendation? Do you go straight NASA or mil spec and always tie any logic high through a 1K resistor, or are you convinced that this is no longer needed? Are you confident that, with enough decoupling capacitors and other transient reduction techniques, it just precludes the need for any of this protection? Or has, a hard tie to VCC ever come back to bite you? Did you ever have a circuit that you had a problem with, and it turns out that, you blew a gate out because it was a hard tie to VCC and you had a little spike come along the power supply? So I'm curious to see what others think about this. I buy cards from the S100 group, and a lot of those will still use a tie-up resistor on inputs, just like old school. But of course, most of the people designing those are old school people. So what are the young folk doing today? All right, well, that's it for this video. As always, subscriptions and thumbs up are appreciated, and let me know your thoughts on tying things high or your thoughts on that asymmetry for common emitters. Okay, I will talk with you later. Thanks for watching. Bye-bye.